Very happy to see you.
Thank you,
How
Patrick.
you doing?
Great to see you as well. So it is a really exciting time at this intersection of artificial intelligence and power, right? We just heard about fusion and what the exciting advancements are there. But this space in fission, nuclear energy, the current technology, right, we're deploying, is so rapidly changing. They actually asked, oh, where are your slide notes? I said, there's so much that's going to change in the next 24 hours that, trust me, we can't do slide notes. So let's start with what happened Monday. So AMD and Oak Ridge National Laboratory announced a huge partnership to deliver the American Sovereign Cloud, right, which is a very large multi-billion-dollar partnership. Jensen announced yesterday a 100,000 core, or 100,000 GPU machine, sorry, called Solstice, which is a multi-billion-dollar machine that will be deployed at Idaho National Laboratory. Google announced a partnership to restart a nuclear power plant in Iowa yesterday. So that's what happens in 2 days in this space. And there'll be more announcements today, I'm sure. In fact, the slides, there's always a few different versions of my slides, and there's a different version, that we always don't show. So anyway, so we'll dive in and kind of level set where we are as an industry and where things are moving and how we can use AI to rapidly transform how we deploy fission, which ultimately has applications to fusion and other technologies as well. So as we dive in, our laboratory, so raise your hand if you're a little bit familiar with the Department of Energy laboratory system. Okay, a few of you. So it's the largest scientific workforce in the world, right? It is a 78,000 people. It's a very large system. Our laboratory, we're mainly focused on nuclear energy and technologies to really deploy that forward, and then also technologies for fusion like tritium blankets and things like that. Of course, like any lab, we're a $2 billion national lab, so we do a lot of things outside of fission 2 and national security. And we are also heavily involved in semiconductors. So actually, Dassault is partners with us on an institute called Smart USA, which is $1 billion, yes, which is a $1 billion institute to basically bring semiconductor manufacturing back to America. And that is a huge partnership to accelerate semiconductor manufacturing. So when you think about AI, there are really two problems that I am focused on. And we'll talk mostly about power. But the second problem, which we presented at Dassault's event, I don't know, maybe it was about 4 or 5 months ago, is semiconductors and what we can do to accelerate deployment of semiconductor manufacturing here. So those are the two problems that I spend every day thinking about. So if we move forward, the other thing that's happening is we have unprecedented support from the White House. So nuclear fission, right, wasn't always as popular as it is today. But today it's at an unprecedented level of popularity. It is one of the few issues that's bipartisan. Everyone agrees nuclear power is part of our future. And so is fusion, and so are other technologies. It's important to mention to deliver the AI power demands we expect we're going to need, which Eric Schmidt, the former chairman of Google, estimates that's about 100 gigawatts of power between now and 2030. That's an incredible amount of energy. And you're not going to get there with one technology. But we think fission's a key technology that's going to enable that transition. So there are 4 executive orders that President Trump signed. The first, right, is to reinvigorate the nuclear energy base. The second was to reinform nuclear reactor testing at DOE. So that's specifically, right, how we do testing at Idaho National Laboratory, deploying advanced reactor technologies for national security applications at Army bases around the country, and then to reform the NRC. So for those who are not experts at regulatory reform, it is important to understand how things have operated for a while. In fact, there have been examples from AI founders of like how not to do it when it comes, and these are the NRC as an example when it comes to AI. So the NRC, right, they can kind of set rules as they see fit. So like the Vogtle power plant, they changed the rules in the middle of the development of the power plant. So that power plant went from a $14 billion cost to a $28 billion cost for one power plant. So just think about that extreme cost, right? So we need predictability. Not that we need regulation, right? We need rules, we need people to assess the safety of these facilities, but we also need to have predictability in those timelines. So that's what this executive order did, was it put an 18-month timeline on the NRC to either approve or deny an application of a new power plant, and a 12-month timeline for existing power plants to approve or deny those applications. So it's really important to have those predictable aspects when it comes to attracting the investor community to deploy 100 gigawatts of new energy, which, by the way, the president estimates we're going to need to deploy 400 gigawatts by 2050. So that's an incredible amount of energy demand that we're going to need to fulfill. So the next thing is DOE announced, and this you may be less familiar with, maybe a few of you were familiar with the executive orders since those were kind of a big deal in the news. This maybe you're a little bit less familiar with. So DOE also announced site selection for AI data centers using national lab facilities. So they selected 4 locations, Idaho National Laboratory being the first, but there's also Oak Ridge Reservation out in Tennessee, the Savannah River site, that have all been selected to deploy data centers using DOE land. And what's big about that is then you can use what's called DOE authorization, which is a different process than NRC. So it's using a federal process, which is more like what's done in the UK, where it's a collaborative regulatory process that looks at new technologies, and it's more technology-driven rather than rule-driven, if that makes sense. It still assesses the same level of safety, but it uses a much different process to do it. So that's important. And so we actually have what's called a request for application out right now for partners to look at deploying their facilities on these DOE sites, and those are due next month. So we will hopefully have announcements soon of who's deploying new data centers at large scales. And like I said, you saw the beginning of some of those announcements this week with Oak Ridge announcing their new machine on Monday and Argonne announcing their new machine yesterday. So more to come. So the other thing is our lab is big, right? I mentioned $2 billion, right? So again, we focus a lot on fission. Those top things on our list, right, are all around fission technologies, right? Nuclear, obviously, is all focused. It's called nuclear science technologies, all focused on nuclear energy, right? Integrated energy is really how we focus bringing nuclear with other energy technologies that also bring us to the future we need to get to. And then the third part, national security, how do we secure it? But the fourth part are kind of our emerging areas. We call these mission agility areas. One is fusion, which ties well with the prior presenter, Alex. The second is space and defense fission. So looking at getting power into orbit, think of the moon. We're working on technologies like that. Critical materials, where do we get the materials to make these facilities? Uranium at this level of production. And then, of course, AI. And I personally, as you probably can guess, lead the fourth part of the laboratory. So we're very focused on AI applications for all of those other areas of the laboratory. And then, of course, we also work broadly with other partners around the world. So fission, where are we on fission? So for those that are experts at the technology, you might say, well, there hasn't been a lot of new fission plants in the US. There's only been a few, right, in the last 10 years. Well, this is where we are today. So to get on this chart, there's certain criteria you have to meet to be included. And so these are not every nuclear energy project, but they are the ones that we have selected to be on this timeline chart. And you can see as soon as next year, there will be new fission power plants that are starting up. In fact, there are 11 that were selected for the Reactor pilot program. And we don't think every single project will be successful, but many will. And so the president, by July 4th of 2026, is expecting to start criticality of at least 3 fission power plants. So that's pretty much light speed in fission space. We're using new processes to make that happen. Many of us work 7 days a week to make this process a reality. We have a dome test bed that is under active construction right now to place these first test beds in. So these nuclear reactors go inside of a dome, right, so that there's a safety boundary around them for these first demonstrations. These are advanced reactor technologies, right, so these are not your typical light reactor plants. Then Oklo, which is Sam Altman's, he founded this company for fission called Oklo. So their Aurora testbed comes out in 2027. That's also when ALO and Hermes is at the Oak Ridge Reservation, ALO at Idaho National Laboratory are also expecting to deploy. In fact, Aurora, the Oklo folks, did their groundbreaking about a month ago. Project Pele is DoD's microreactor technology. So why is that interesting? Imagine being able to deploy nuclear technologies in the field and not have to truck diesel. And why is that important? About half, 40 to 50% of deaths are actually trucking diesel. So being able to save veteran lives, that's a huge deal. And so that's why we're really excited about technologies like Pele. And they use what's called TRISO. So it's a ceramic particle. So the nice thing about TRISO is your fuel is actually contained in these pellets. So the worst case scenario is you have some pellets you have to clean up, but it's all contained within these ceramics. So it's a very safe technology. And newer, it's actually technology that we helped invent at Idaho National Labs. So anyways, and then there are, later into the decade, you can see other projects like the XE100 from a company called X Energy. And we'll talk a little bit more about that in a minute here. So X Energy has an investment of a $500 million from Amazon. So we've seen an unprecedented interest, obviously, from all of these different AI companies, Google included, who presented first this morning, to invest in this area because they know they're going to need the power. So Amazon has like I said, that $500 million investment in X Energy, but also a wider influence. We talk to Amazon on a daily basis. Microsoft has their own billion dollar investment in restarting a unit at 3 Mile Island specifically only for AI data center use. And they also have their own AI technology for nuclear licensing. So it's Gen AI to develop licensing documents for nuclear energy, which is pretty cool. We partner with them to take that technology forward. And then Google has a partnership with Kairos Power, but like I mentioned, they're also restarting a 600 megawatt plant in Iowa as of yesterday. So, and there will be more announcements to come. In fact, this slide I can never keep up to date. NVIDIA has an investment with Ventures with TerraPower, which is Bill Gates' reactor company. Oklo has a 12 gigawatt partnership with a data center company called Switch. I could go on and on and on. But these are the announcements that have been happening just in the last couple months. And Meta has been seeking about 4 gigawatts of new nuclear power. So many of what we call the order books of these fission startups are in the dozen, sometimes more gigawatts of power that they have to produce. The last presenter talked about the idea we need to get to thousands of fusion power plants. The same thing is true here, right? To get economies of scale, you've got to achieve a higher level of capacity. But we're not going to be able to get there by using classical technologies. I was talking to someone at a table a few minutes ago, and by just grinding and sitting down and working with Word and PowerPoint to get these power plants done. That's actually, by the way, the #1 most used tool to design a power plant is Microsoft Word. I highly suggest not using Microsoft Word to design your power plant. But that is true. And if you were to walk to any startup today and just look at the computer screens, you will see Microsoft Office everywhere. And it's nothing against Microsoft, right? We partner with them when it comes to AI in this space, but it is not a great way to push the ball forward. So how do we get there? So the nuclear energy outlook, right? We talked about the need for 300 or 400 more gigawatts of nuclear power. The national labs partnered together on an AI for energy report, and it has 8 chapters in it. This is public, you can pull it off the internet. The first chapter is on nuclear energy AI. And that's not because it's alphabetical, that's because we thought that was the area where we had the most potential to make a difference when it comes to AI at the energy sector. The Secretary of Energy from this administration has called for abundant nuclear energy and rapid deployment of nuclear energy. Again, we've seen consistent, strong support for nuclear across the aisle from both parties for a long period of time. And so to that working smarter comment, how can we use AI to accelerate nuclear power deployment? And of course, in a very safe way, I would argue in a safer way than we've done historically. And there are 3 use cases we'll talk about, and then we'll talk about how to bring it all together in a capstone. So the first is accelerating deployment and licensing. So on your left, you'll see a really simple example, right, where you can type in some text, and it will generate for you autonomously what's called IFC, Industry Foundation Classes CAD, that is compliant and will work in this particular case, an Autodesk tool, but it will work in any tool. It would, of course, import, I believe Dassault's products have support for IFC these days. On the right, I don't know if they'll be able to play this video or not. We'll see if they can, behind the scenes, use a mouse. But on the right, you'll see an IFC file that can then be autonomously meshed and converted into our seismic analysis tools. So why is this important? Imagine an agentic loop where you prompt and then you go through a whole loop to design the power plant, and it links. So the national labs, there it goes, all have these codes that do the assessment on these reactors. And I still remember 5 or 6 years ago, someone said, it's impossible to automate all of this. Well, we've been sponsoring a bunch of PhD students, and it's not impossible. We've gotten to the point where we can automate many of the steps in the process. And of course, this is before transformers, before large language models. Now we know we can do much more. I personally have been working on code over the last, yes, I still code. I hope many still get that opportunity. I have a tool that automates fault trees, right? You take a PNID, which is like a 2D diagram, and it builds you a fault tree automatically and does all the calculations correctly. Which, if you use an LLM out of the box, it will do some of it for you, but it always gives a wrong answer. This gives you a much closer to correct answer within 5 minutes. Now, you as a human, you still have to go through and do the human analysis part. You still have a job to do, but it shortens the timeline, right? So you can automate a lot of this entire loop. So working with our partners, right, the labs, we don't build commercial products. So we have close relationships with companies like Dassault to bring these products to market and to also integrate with existing CAD products and tools that we need to make this possible. So the second part is autonomous laboratories. So you think about the materials science and the fuels that go into these advanced reactors, right? They operate at higher temperatures a lot of times. And so maybe we'll talk a little bit about, for those of you who aren't experts at fission, right, it can be confusing, right? Well, wait, you're going to deploy more nuclear power. Sometimes I used to get questions like, is that safe? What does that mean? So advanced reactors, what separates them from traditional light water technologies is that they're passively safe in a lot of cases. So that means they have a negative reactivity coefficient. So as it gets hotter, you get less reactivity. And that's how a sodium-cooled fast reactor works, which is the technology that TerraPower and Oklo and many others are doing. And we already talked a little bit about TRISO, which is that concept of those ceramic particles, right? Which is a different technology, but the same idea, right? That everything is stuck in these little particles. So the worst case scenario, again, you have some pebbles. You got to clean up the pebbles, but it's not a huge issue as it could have been with earlier, older technologies. So, but to make those technologies a reality, there's a lot of complex science that always has to occur and is still occurring now. So how do you make TRISO economically viable, right, and manufacture it at large quantities? So that's something we've been partnering very closely with industry on. How do you accelerate a new material, right, again, that can withstand higher temperatures, or you can qualify it? So traditionally, qualifying a material might take like a decade. We're hoping to have that amount of time by using robotics in these laboratory environments, where normally it would take a human, a couple hours to do a process, shorten that down to 30 minutes, and then replicate that many times over. So again, this is something we just started this October, but we already have the robotics investment. They're already working. Now we're starting on the AI investments of how can we bring automation into our own laboratories. And then the third part of the challenge might be the most obvious, which is how can we get control of these reactors in a safe way that uses some level of automation and AI. So 3 years ago, we announced the first autonomous non-nuclear microreactor. So for an hour and a half, not for days, but for an hour and a half, there were no humans that were allowed to control the reactor. It was all AI controlled. So for 10 minutes into the future, it would forecast on its own what the temperature values would be, and then it would control the reactor based on the future forecast values. Obviously, doing process control in real time is something that actually happens on a lot of power plants today, but doing those forecasts 10 minutes out or more into the future and using accurate control is actually something that's this is the first time it's been done. And then you might ask, well, how many times did you get to train the model? We had one shot. So that exact facility was very fragile. It was a testbed environment. So it was a one-shot job, and it was 0.3% off. The only thing it didn't detect was a human operator clicking the wrong button. On the right, we did a real fissile reactor. So this is called the AGN-201, 5 watts of power, so relatively low power levels. Again, 5 watts, not kilowatts, 5 watts. Think of a light bulb. But the reactor the core is maybe a little bit smaller than this table. The vessel is probably as long as your arm width is. So it's still like a sizable facility, but these were designed for universities to teach their students. U2, back in 1965, could have a nuclear reactor for $100,000. So the idea was to be able to make these available to students, and now we're using these same reactors for teaching to be able to do these experiments, to bring digital twins. So this reactor stream real time to the cloud and use predictive analysis to figure out what the state would be. It is now, by next year, going to be under remote control. So using the cloud to remote control a reactor at small power levels, right, within a safety envelope. But we're moving to a remote control, which we think will unlock the ability. You could imagine a NOC controlling many reactors at the same time, having a combination of AI at the edge, so you can control there, and then AI remotely, right, with humans, right, still in the loop in that process. So, so we'll take a look in a little video of what one of these kind of processes looks like. There we go. So this is our magnet test bed. So you can kind of see an idea 3 years ago, kind of what that actually looks like. So you can see those little triangles are when AI actually took control of the facility. You can see with a HoloLens demonstration here in a second what it kind of looks like from an operator viewpoint, right? They can see in a hologram real-time temperature values, prediction values. And again, this is 3 years ago. It takes us a while to make these videos and get them released. So, so you can imagine this technology is evolving rapidly. And then of course, at the console, you can actually see on the right, that's Katie, she's a machine learning scientist. On the left, Logan is actually the one who made that visualization, but for the purposes of the video, he's sitting at the table. But you can kind of see what an operator would see while all this is occurring. So none of them were able to make any human control, right? All this is happening in real time through machine learning. So Patrick, I think that brings us to a good time. We have 5 minutes left to do some questions. I always like a little bit of interaction. So we'll do that. We'll skip that slide.
Thank you, Chris. And indeed, time for questions. So any questions from the room? Let's start with the room this time. I think
Quiet?
Your talk was very clear. See, one question over here.
Are you also working on how to manage the waste of nuclear fission?
Yeah, so that's a great question. So how much waste, does anybody know in the audience, how much waste all fission power plants since they've started in America actually generated? We'll say high level waste, right? Waste that takes a while to deal with. It's a single football field, 10 feet high. That's it. So the amount of waste that is generated from all fissure plants in American history is actually relatively small. Now that said, we are working on that problem, right? Yucca Mountain was a solution that has been talked about. I think there are ongoing political conversations as to what that will be long term. But I will say right now, most of the waste is actually stored on site within that fission power plant. But it's actually not as big of a problem as you might think, right? A football field is not that big. But it's a good question.
Question over here.
Yeah, fascinating presentation. So, in the AI factories that are coming up very rapidly, so how far are we from the kind of semi-portable nuclear power plants, that will make the operation of the AI factory completely self-sufficient or technologically?
So that's a good question. And some slides I couldn't put in. So let's see. So what I can say is that the microreactor technologies, right, you'll see the first ones next year. You'll probably see the first commercial, like you could buy one in 2027. Now from a factory, right, being able to produce many of these, Radiant announced that they're starting up a factory in Tennessee right now. And Radiant, by the way, is another microreactor startup. And so there are companies that are already putting online factories, and they're talking about 50 per year that would come off the factory. And these are for smaller plants, so these are at single-digit megawatts. For the larger plants, that's where AI comes into handy, because what I think most people don't think about is that, like, for a small nuclear power plant, it's kind of like building a plane. You could build the same one every time the same way. For a larger power plant, think of the building we're sitting in. There is no other building like this in the world, right? Exactly the same. There was no building, probably many of you stayed in a hotel, right? There is no exact hotel with those exact dimensions anywhere else. And you might say, why? Why is that the case? The reason is the seismic profile, even in like Manhattan, is different at different parts of Manhattan. The feed water has different situations in it. The local regulations have differences. When you add all those things together, you end up with slightly different configurations, if you will. And those differences are what makes it harder to print them. But that's where AI comes in, to do that, what we call balance of plant automatically. But good question.
Over here, a lot of interest.
A really great presentation. Just a question about distribution. Is there any work going on to upgrade the grid to handle the distribution of all this power? I guess there's also EVs coming along, and yeah, would love to hear your thoughts.
So yes, there is work going on, but it is an ongoing problem. So when you think of energy, right, we talked about it as one of the biggest problems that AI faces right now. Right? I fully believe in Google and our Silicon Valley partners that they'll be able to get there from an algorithms perspective and a data perspective. What I think right now we have a huge challenge is energy, right? We talked about the generation, which is nuclear, but we didn't talk about the transmission. So Colossus, if you're familiar, which is Elon's supercomputer, right, that he built in Memphis. Do you know how they got their power? Diesel generators, 430 megawatts of diesel generators. Just to put that into like context, it's like, we throw out numbers like that and it's like, what does that mean? That's 2/3 of all the diesel generators in the United States in one place. Not to mention the city of Memphis isn't really like thrilled about all that diesel generation happening in their backyard. And so the reason they had to do that was because they couldn't get transmission lines to go run 2 miles. And it just would have taken, I think he said 2 or 3 years. We met with the Colossus team. But so these are ongoing problems that we have to also resolve, the transmission. Now, nuclear energy unlocks one thing which you may have thought about, but I didn't say, which is behind the meter. So you can deploy a fission plant right next to your data center, and you don't have to deal with the transmission problems. You can do your own microgrid. So that's an option that gets unlocked.
Okay. Any final question? No? Let's thank Chris for this presentation. Thanks a lot.